So we're going to start our story in space. As you probably know, back in the 50s and 60s, a computer would occupy a whole room. It'd be made from valves, and the Apollo mission, really pushed the boundaries of what was possible with computers. And MIT, Raytheon, NASA, they squeezed down a computer into something that's the size of carry-on luggage. It weighed about 70 pounds, so pretty weighty stuff. Consumed 55 watts of power. And that number is important because you're not going to plug this thing into the wall. They had to develop a fuel cell to sustain it for the mission. And you look at the capabilities. It's roughly under 100K of RAM, ROM, and the clock source was 2 megahertz. So this and then was divided down. So kind of not the most performant of machines by modern standards, but very advanced for the time, and took man to the moon. So obviously a fantastic feat of engineering. So if you look at what can be done today, and this isn't a sci-fi thing, this is a chip that's out there, was announced earlier this year. Comparable performance and memory is now achievable in something that's about 2 millimeters by 1.6 millimeters, and this is a golf ball. This isn't the moon, right? So this is tiny, tiny little thing. And actually, if you catch me later on, I can show you this stuff. And the important thing is not just the form factor of the chip. The important thing also is the power that's consumed, right? So, we're not talking about watts or milliwatts. We're now talking about microwatts. So this is extremely low power. And this, for me, this is a 32-bit computer. It can be connected to the internet. It's based on an ARM Cortex-M0, so kind of the lowest, smallest, lowest power kind of processor we have. And this, for me, is why IoT is so exciting, because this stuff now can be embedded into all sorts of new products. I'm going to give you a bit of context on who ARM is and what I'm doing standing here chatting with you. So ARM's story is a pretty interesting one. This is actually prehistoric for ARM. So back in the 1980s, there was a project by the UK government and the BBC to teach the people how to program. And what they did is they funded a startup to create a home computer that would go into schools across the country. And this group of gentlemen made that happen. And for me, this is amazing, because I learned to program on one of these machines. And so I can see the kind of parallels. There was a report written by a lady called Tilly Blythe, who is the keeper of technology at the Science Museum in London. So I guess the sister museum to this one. And what she did is she traced back a whole load of industry, a whole load of innovation and success to the fact that there'd been this education around computers back in the 1980s. And I resonate with this thing because it's my life story is written in this report. And so when I see the maker community and the amount of access people have to computing now, not just programming a home computer, but physical computing, computers that can be interacting with the world around them, I'm certain the impact of what is happening now is going to be tremendous in the next decade as it comes. So yeah, I'm kind of rambling around a little bit, but this is the origins of ARM, because later these guys decided they wanted to develop their own processor. And actually, for what they were doing there, it wasn't a tremendous success as a home computer, but it got a big break because a company called Apple were developing a tablet, and they wanted a really low power architecture to do that with. And so back in the 1990s, they span out a company called ARM to produce this processor for the tablet, which was called the Newton. So remember, this is 1990, this is a while ago now. And they had a mission to become the global standard in technology. And then kind of today, and I'm not even sure how many people, do you know who ARM is? Put your hand up if you know who ARM is. Oh, great. Maybe I should have skipped through this quicker, sorry. So last year we shipped about 10 billion chips. So that's a lot of chips. And ARM is a modest company, and we don't make that much noise about it. And you might wonder, well, how did these kind of, they started in a barn, by the way. That's a picture of a barn in Cambridgeshire. So it's kind of roughly equivalent to a makerspace in New York, if you translate it to here and now, maybe. But yeah, 12 guys in a barn with this mission to be a global standard in computing, to shipping 10 billion. There's a couple of good reasons they got there. One is collaboration, and I know this is a kind of overused word in some ways, but it's absolutely fundamental to the way ARM does things because we don't make the chips. So we work really closely with our partners. Like you got some names up there that you'll see at the Maker Fair. So Atmel or Texas Instruments or Freescale or Samsung. So ARM designs a core component of this, and it leaves them to go and innovate and focus on their end markets and do what they do best. And it means we don't just talk with the chip makers, we talk with the people using the chips. And from the maker point of view, this is me with the guys at the Maker Fair in the Bay Area, and we were really happy because we won a ribbon, Editor's Choice at the Maker Fair in the Bay Area. And the reason we did well, I think, is because ARM wasn't really doing that much. All we did is invited a load of startups who are doing cool things with ARM technology and just let them talk about what they were doing. What we had iFixit with us too, so they were taking the latest gadgets and just tearing them open and showing everyone what was inside and how you can make this stuff. So I think that's the secret to ARM success, is not just innovation in terms of technology, but in terms of business model and the way we do things. And the 10 billion is a very big number. It's not 10 billion of the same thing. And mobile phones and tablets is probably what we're most famous for being inside of. But that really only accounts for about 50% of those chips. I'm not in the mobile side of the business. I'm on the embedded side, which I think is the really cool side, because it's all the different various projects that span from kind of robotics and drones to, yes, refrigerators and washing machines and all the kinds of stuff in the middle. And ARM is a relatively small company, but we have all these partners making the chips, and we have distribution like DigiKey or SparkFun, or high volumes you might go to people like Arrow or Avnet. And so there's lots of ways that you can get your hands on reference designs and electronics that have these ARM components inside. And so I heard Diego talk about the Internet of Things and the volumes projected. On the face of it, those numbers sound very big. But then if you look at how many chips we shipped last year, and this is just the Cortex-M, so this is just that small low power class of chip I was talking about earlier on. About 3 billion of those were shipped by ARM last year. And again, these are capable of being connected, Bluetooth, Wi-Fi, Zigbee, not necessarily all IP addressable today, but it shows you that that kind of scale could be achieved. And I think this is, for me, the really important point. I'm a computer science guy. I'm not a product designer or an artist or a farmer or any of the people that may be really benefiting from this technology today. What I have done, what ARM has done, is produce this stuff at a low enough cost and made it available enough that guys like Arduino and Raspberry Pi have chosen to put it in their platforms. And I'm really humbled to see the Arduino Zero that was released earlier on this year. And for me, the most exciting part is when people from beyond electronics engineering get to grips with this technology and do creative things with it and apply it in ways that have not been done before. And of course, Raspberry Pi, we were talking earlier on. So this stuff has got ARM chips inside of it. And it's not just them. There is a load of different development boards. So you've probably heard of Beagle, BeagleBone, BeagleBoard, Odroid. That's like a quad-core, 2 gigahertz kind of souped-up Android machine. Right the way down to, there's Nordic Semiconductor have a little Bluetooth LE module that you can power the button cell battery. And behind this, there's I think it's, over 3,000 standard parts, 3,000 different chips. But fear not, the architecture is still ARM, so the software ecosystem around this is pretty much standardized. And you might say, well, why do you need all these different chips? Well, I think it kind of goes back to the original point that if you're doing something on the cloud or on a desktop machine, you're tethered to the wall, you kind of know what the I/O is, you know what the constraints are. But if you're creating an internet-connected thing, an object, that is not plugged into the wall, you'll often find that the battery is the biggest bulk inside of that enclosure. And it's going to have a lot of impact on the usability and features and functions that you can put in there. So, ARM's background is mobile phones, and these aren't hard and fast numbers, but it's an kind of idea of what kind of capacity battery can you fit in these types of devices? And so, 3,000 milliamp hours for a smartphone, and then wearables, a smartwatch might be 300, 150 milliamp hours for kind of more exercise trackers and activity trackers and that kind of stuff. And I suppose the point I'm making here is when I was talking about power numbers for the processor, this has, if your electronics is consuming 300 milliamps and you have a 300 milliamp hour battery, you can kind of work out, well, that's going to last you an hour and maybe that's not great. So paying attention to the energy is very important. And so as a little bit of an example, I'm a big fan of iFixit. This is, I don't know if Scott's in the audience, but this is the insides of a Pebble watch. And what you'll notice is the PCB, really well designed, really compact dimensions. The profile is very low, so you can squeeze in more stuff into the case there. And the battery is really the biggest thing in there. And that's 130 milliamp hours. And so when you're designing this electronics, the reality is, there's lots of variables you can tweak. You can put it in standby modes. You can make sure that the duty cycle is minimized, so you're only active for the minimum amount of time necessary. And you're really trying to minimize the area under that curve to get the most life out of your product. And so, paying attention to this, and the professor from Cornell made this point yesterday. What is the best way to do this? How do I optimize my design? You need to do a bit of research and work out how you can do, meet those objectives with the most appropriate technology for the product. And if you do that, you can squeeze it into things that no one has ever tried or imagined. And this is, I think, where we're seeing the Internet of Things push the boundaries of where we're getting computers. So obviously software is a hugely important aspect of this. So, I'm talking here about some of the really tiny devices, and for that we have, obviously Arduino supports Cortex M0 and M0 N3 with the Duet. Python you can run on a Raspberry Pi. I mentioned Android on the Odroid. Mbed is a project that we have within ARM which is focused on the Cortex M devices and kind of with a view to enabling Internet of Things. We know that there's an integration of sensors and microcontrollers and communications, and with the kind of libraries to support this quick innovation with ARM-based micros. So software is hugely important. Having that big ecosystem of providers means that the tools, the OSs, the programming languages that you're familiar with are supported on the ARM architecture. And actually, Raspberry Pi used my slides earlier, so I'm going to skip this. But and they actually had the physical thing, which is kind of outdoes me. But module form factors are obviously very important getting to production as well. And you're going to see this increasingly, modules with embedded wireless, and already today there's Bluetooth LE modules, Wi-Fi modules with ARM parts on. Okay, so that's a kind of background in terms of what ARM is up to in this area, and you've seen a lot of kind of, I guess, predictions on where all this stuff's going to go and what you could do. I thought I'd go into a little bit of depth into what people are actually doing today. I was going to start with this thing. So there is a company called Proteus Digital Health, and their CEO did a presentation at the Wired Health Conference earlier this year, and I would definitely recommend checking this thing out. They have a patch, a wearable patch, and they have a swallowable medical device, and this is crazy. So it uses anode and cathode on the device. You swallow it, and it uses your stomach acid as the battery acid to power the thing. Obviously, it's wireless, right? You don't want to retrieve this thing. And then communicate your temperature and pH to the sensor. A company called Estimote, actually based in New York, and they announced this thing yesterday, have created beacons based on, again, it's ARM Cortex M0. It's got from a company called Nordic Semiconductor using Bluetooth LE, and it allows you to create context-aware applications. So if you're walking around a store, it'll know what products you look at, and even these tags are not just beacons; they have sensors, so it knows: are you picking up the product? Are you turning it upside down? How long is the customer interaction with it? All kinds of interesting things are possible there. Another example, and this is, I was told about this by a company called Electric Imp, and they released a couple of years ago an SD form factor with a Cortex-M3 and Wi-Fi, and with a company called Bonded Energy Solutions, they retrofitted steam-heated apartment buildings in New York. And you know, obviously I'm not from New York, so I don't know how your experience of this is, but you know, I've been told that there is a lot of these kind of Victorian apartment buildings with a steam boiler in the basement, and in the winter it gets so hot that people just open the windows because they can't control the heat. What these guys did is they took this electric imp and they retrofitted to the valves of the radiators in the apartments, and then they also communicated that back to a hub that was controlling the steam boiler in the basement. And they, you know, optimized the efficiency, got the tenants more comfortable, and reduced the amount of energy consumed. So this is, I think, really cool. And actually, you know, talking about Internet of Things, like some of the snazzy consumer stuff that's possible is interesting, but I think the biggest gains will be retrofitting the crusty infrastructure, which has been there for decades or centuries, and reinventing that stuff and retrofitting that stuff. So I think this is a really interesting example. Smart cow was just shown in the last presentation as well. I can't believe my luck. So this is a real example, and this cow does have an ARM processor attached to it. I don't know how much detail I can go into about this, but the sensor got in there somehow, and then you have a smartphone reading. We'll skip over this one. Okay. So in terms of consumer devices, you know, I see a lot of Kickstarters that are doing, you know, pretty amazing projects, and Pebble Watch is a, you know, really famous example of kind of leading the charge in terms of wearables and making a consumer device there. And you might wonder, well, you know, on Kickstarter, on Best Buy, what's inside these things? What are people using? How are they creating it? iFixit do a really good job of doing these teardowns for me. You know, I used to actually, my first summer job was in a TV repair shop, and as a kid I'd open up a lot of stuff. I don't do as much as I used to, but iFixit, I definitely recommend their website. Not least, I spilled coffee on my laptop the other weekend and I fixed it thanks to their toolkit. So I shouldn't plug them too much, but you know, stuff like I think this is the Samsung Gear Fit. So what they did is they take apart the device and then they give you a little rundown of the bill of materials in there, and you can see, you know, the PCB is really tiny, and then if you read really closely, and this is a lot of my job at the moment, to check what chip, I know I'm a geek, but check what chip is in there and what's running inside. And this one's a Cortex-M4 from ST Microelectronics. You'll have to take my word for it or look at the website. But if you were to look at the Fitbit, this is a Cortex-M3, and then you've got Bluetooth as well, and then obviously an accelerometer to measure the motion. And this stuff will connect to the micro. This one is really cool if you haven't seen it. So Anki Drive, the little robotic cars that kind of drive around on a track on their own. That's all right. There's an ARM processor in that somewhere. So these little cars have got a little Cortex-M0 microcontroller in them, and I helped launch the M0, so I'm pretty attached to this little guy here. But anyway, yeah. So this is from Anki. And then drones. I really want to get my hands on one of these 3D robotics ones, but then my girlfriend said I had to train with a little drone first. So I have the top one here, which is a Hubsan 4X or X4. Really, really cool little drone for $50 actually. And then I didn't find a teardown, so I just opened this thing up, and this is Cortex-M0. And I'll probably graduate to one of these. And this is the Iris Plus, and the Pixhawk flight controller in this thing is based on the Cortex-M4. And you know, stuff like the Follow Me, they have a GPS module in there, and then associated with Android device, you can get the thing to follow you in. It's pretty cool. I don't know how I'm doing for time. Finish? I got to finish. I just got that. So you can do lots of things. You can put Linux modules in your drones and have them flock like birds, as this university in Hungary did. GoPro has got a lot of ARM chips in it, and so that's cool as well. Internet of Things. Okay, so you know, we talked about the things part, not the internet part. The point I would like to make very briefly is, you know, the low-end chips start in the microcontroller range, start in the kind of 50 cent to $2, $3 range, and they're more than capable of running TCP/IP stacks. Hundreds of K of memory is more than sufficient to do this. And okay, we talked about consortiums, but there are things like the IETF, famous for IPv4, IPv6, and they have defined these kind of lightweight protocols, including security protocols for these constrained devices. So there is definitely standard ways that you can get this stuff done. That's all I had to say. So choice is important, making stuff efficient is important, and collaboration is important. And ARM is sponsoring the happy hour at the Maker Faire tomorrow, and I'll be with my colleague Mark, who I don't know where he is, but he's like consultant engineer guy that can tell you all about other stuff from ARM. So we look forward to seeing you. Thanks very much.